notice. And this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos, sections 1, 2, and 3. All 51 of those videos have already been published on YouTube in their entirety. Please make good use of them. We are now at section 4, measurement, and this is the 17th of 17 videos, and I am running behind schedule. Section 5, statistics, that will also be behind schedule, January 2025. Hopefully, section 6, algebra, February 2025, we will be able to catch up then. Then in March 2025, relations, functions, and graphs. April 2025, geometry and trigonometry. And by May 2025, vectors and matrices. Disclaimer: this schedule is just a projection which may or may not be fulfilled. It is not a contract with anyone. So as I said, I have divided section 1 into 33 videos. These 33 videos here, they cover the foundation on which the rest of the syllabus is based. So please make sure you look at them and know them well. Also, another reminder that you need to know the times tables 2 to 12. If you don't know that already, you will have to learn it, especially since calculators are not allowed in paper 1. As I said, from section 2, all 12 of these videos have been published in their entirety. Section 3, all 6 of these videos have been published in their entirety. We are now at section 4 at this point, way down here. These that you see here, 1 and 4 and 9 and 14, have been published in their entirety. These others, like 2 and 3 and so on, are only partially published on YouTube. So we are now here, objective 15, which is the last objective in the section, and it is video 17. Once this one is finished, I will publish it in its entirety. So from this section, there will be 5 videos out of 17 published in its entirety. The others will only be partially published, and I will let you know how you get access to that. 4.15, solve problems involving measurements. Before we go on, recall I said in the introductory video that you will need a good math textbook or a set of 2 to get more practice questions. CSEC recommends these here, not all of them, you may need 1 or 2. From that list, what I would recommend is a very good 2-volume set, which is quite adequate for the current CSEC math exam. Here is a picture of volume 1, Mathematics, a complete course with CXC questions by Raymond Tulsi. And this is a picture of volume 2. Another disclaimer: I get no financial or other benefits from the sale of these books. Also, very recently, late 2024, a website with AI interactivity has been made available free of cost that deals with past CSEC math questions only. You can navigate by topics or years, where all questions for the past several years have been worked out for you. If you have a question that you need explained, you can ask AI assistant either by text or voice, and most likely that will be explained for you. This is the URL. Now, this website is extremely important because you may know everything in the syllabus, the objectives, but you still have to learn how to answer the questions the way CXC set those questions. So this website is very, very important, especially as we are looking now at section 4, the last objective in section 4, solve problems involving measurements. So remember I said you can navigate by topics. So you can enter problems involving measurements, and the problem that CXC set involving measurements over the last several years will appear. You will browse them, you will listen to them, you will ask AI assistant questions. The home page for that website, RSC, is shown on the next slide. That, as I said, is the URL. I will list that URL in the description of this video below. So all you would have to do is click on the URL and you will be redirected to this site. This is the home page for now. It may change later. You will first have to register, and subsequent to that, you will need to sign in. So from section 4, this is a print screen of the first page. We have completed these 4 objectives. And then from the next page, these 5 objectives. And we are now on the last page from section 4. We have completed these 5 objectives as well, these here. We are here, objective 15, which is like a summary of what we have been doing, where it says solve problems involving measurements. So we are here, as I said, end of section 4, last objective. Just a reminder that for the exam, CSEC Math exam, you will be given a formula sheet. This is the top part of the formula sheet, and this is the below part. So you don't have to memorize these formulae. Just make sure you are familiar with them, how to use them, and when to use them. As I said, we are now here. Solve problems involving measurements, and we have some explanatory notes. Perimeter and area of compound shapes and volume of compound solids. In this video, we will consider 5 fairly difficult questions in order to establish a mode of attack to solve such problems. Many students look at these questions and they look complicated and they say, I can't do that, and they give up immediately. Now, that's not the attitude. What we will do here is we will try to devise a system that you can use so that if you look at these questions and they look complicated, you will be able to use this approach to work through the questions, solve problems involving measurements. Now, these types of questions involve analysis and synthesis. Now, that's just a fancy way of saying that you will need to break down the problem into little manageable parts, do the little parts, and then use or combine those answers to arrive at your final answer. In computer programming, it's called the top-down approach, which is divide and conquer. So you divide a large problem into little parts, work through the little parts, and then take your answer from the little parts, see what you need to do with them to arrive at your final answer to the original question. You must determine the sequence of steps you will use, that is your approach, before you begin your calculations on the question. In other words, understand what the question is asking and how you intend to get to the answer. This is where most learners run into difficulty, since they start out on a journey of solving the question without knowing beforehand how to get to the destination. Now, do not skip this first step, as it is crucial. Example 1. The cross-section of a 40-meter long community pool is shown in the diagram at right. So this is the cross-section. Remember, it is 40 meters long going back that way. After a total drainage and cleaning, the tongue wants to refill it to 25 centimeters from the top. At what rate must water be pumped into the pool to fill it in 24 hours? State your answer in cubic meters per hour. Correct the three significant figures. As I said, on first reading, it may look kind of complicated. So let's look at our plan of attack. We will employ something called reverse engineering. We will develop the steps backwards, then work towards our answer. So we know the time. It's 24 hours. We want to find the rate of flow, cubic meters. Now, if we know the time, which we already know, we need to find the volume of water to be pumped into the swimming pool. To find the volume, we must multiply the cross-section, the area of the end of the water, not the pool. Remember, there is a 25 centimeter space above here that you will not fill. And then once you find the cross-section that you are seeing here, once you find this cross-section, you will multiply by 40 to get the volume of the pool. The cross-section that you see up here is a compound shape made up of a rectangle at the top, which is 15 meters by 1.25 meters. That is this rectangle here. Remember, there is a space that we have to leave out here, 25 centimeters. So if you take out 25 centimeters from 1.5 meter, you get 1.25 meters. And the length this way is 15 meters. So the area of that shape will be 15 times 1.25. And then you have a trapezium here. This side down here of the trapezium is 4 meters. And this side here would be 15 minus 6, which would give us 9 meters. The distance from here to there is 2.0 meters, because remember, from here to up there is 3.5, and from here to up there is 1.5. Subtract that 1.5 from 3.5 and you get 2.0 meters. Okay, so we can use that to find the cross-section, which is, as we said, 4 meters by 9 meters. That's the parallel size of the trapezium. And the perpendicular distance between them is 2.0 meters. So let's work backwards now. We will work backwards to get our answer. So now we know what we are doing. We know the approach. We have reversed engineered this question. We are going to begin from what we know, work backwards, and then start working from there to get back to our answer. So let's see. Firstly, we are going to find the cross-section, and then after that, we will multiply by 40 to find the volume. So the cross-section is 15 meters times 1.25 meters. That is this part here, plus half of the sum of the parallel sides, half of 9 plus 4, and multiply that by the distance separating the parallel sides, which is 2. When we work all of that out, we get 31.75 square meters. That's the area that you see here. Not right up to the top. Remember, we have to leave out 25 centimeters to the top of the edge of the pool. So that is the cross-section. We now need to multiply that by the length to get the volume. So we multiply the cross-section by the length and we get this volume, 1,270 cubic meters. That water has to be pumped into that pool in 24 hours. So now we will divide that volume by 24 hours and we get this amount cubic meters per hour. We're almost finished. State your answer in cubic meters per hour. Okay, we already have that in cubic meters per hour. The three significant figures. So 1, 2, 3. You round off where that 9 is, which gives us 52.9. And since you are rounding off at the 9, you take half of that position, which is 1/10, and you get 0.05. So this is our answer, 52.9 plus or minus 0.05 cubic meters per hour. Wasn't so difficult once you understand what it is. The next one will be a little more complicated. But remember, if you understand this and you get the approach, then any simpler question that CSEC asks you, you will be able to do comfortably. Now, if you find this video useful and interesting, please like and share. That is, like and share. You may also consider subscribing to this channel. All right, we go on to example 2. A cylindrical tank with a tall conical top and a flat base is made from steel that is 10 millimeters thick, that's 1 centimeter. If the outside diameter of the tank is 1.45 meters, its total outside height is 4.3 meters, with the cylindrical height being 3.0 meters. Calculate its mass given that the density of steel is 7,580 kilograms per cubic meter. State your answer in kilogram, correct the 4 significant figures, and you are given that density is equal to mass over volume. Now, if you are not given a drawing, make a drawing. If you are given a drawing, consider the drawing carefully. So this is the cylindrical part, 1.5 meter outside diameter. Its height is 3 meters. That's the height of the cylindrical part. We also have a conical part here. The total height, including the cone, is 4.3 meters. So plan of attack. We will do reverse engineering. We will develop the steps backwards. So we know that density is equal to mass over volume. We want to find the mass. We are given the density, which means that we need to find the volume of material used, the volume of the steel used to make this tank. If we find the total volume of steel used, we can substitute it in this equation at the top here, as I said. Mass is equal to density times volume. To find the volume of the steel, we will have to find the difference between the outside and the inside volumes, not forgetting to add the base. So the outside volume, let's find the volume including the thickness of the steel. Pi r square h for the cylinder plus 1/3 pi r square h for the cone, and we haven't dealt with the base yet. That's the outside volume. Then we can find the inside volume. It's pi r square h, of course, of the inside now, plus 1/3 pi r square h, and now we're dealing with the inside. We are going to have to subtract the thickness of the steel. So now we also have to find the volume of the base, which is pi r square h, which is a disk down here. So let's see. We will work backwards to get our answer. So now we know what we are doing. We'll find the total inside volume. We'll find the total outside volume. We subtract the inside volume from the outside volume. And then we will relate that to the equation we are given. Density is equal to mass over volume. We know the density. And then, by then, we would have the volume. We will be able to find the mass. So volume of base, just the base, it is pi r Now, if the diameter is 1.45, then the radius would be half of that. We will square that, and we will multiply by its thickness, which is 0.01 meter. And so the steel used in the base is this. Now let's find the inside volume. Now you have to be a little careful here, because this radius for the cylinder itself is no longer half of that. You will have to subtract from 1.45, you will have to subtract 1 centimeter from this side and 1 centimeter from that side, and then divide by 2. And so you get 0.715 here. Here as the radius, you square that. The height inside here, recall that we also have to subtract a centimeter from down here. So instead of it being 3 meters, it is now 2.99 meters. So that this here will give us the inside volume of the cylinder here. We still have to find the inside volume of that cone up there. It is 1/3 pi times the radius, which is same 0.715 here, half of that to be this, times the height. Now you may think that the height would be the difference between 4.3 and 3, and so it should be 1.3. However, this top here, there is a little thickness here. We will subtract the thickness of the metal from the top there, so we get 1.29. That's an estimate. It's a little more than the 10 millimeters, but we will use the 10 millimeters. And so if we find this part here, we get the inside volume of that cone. Add the two of them and we get a total inside volume. So now we'll find the outside volume, but we need to be very careful here. Outside diameter is 1.45. So the outside radius will be half of that 1.45, which will be 0.725. But this height from here to there is now 3 meters. You have to take out that 1 centimeter thickness for the base. And so you get 2.99 meters. So this will give us the outside volume of the cylindrical part here. And now we have to find the outside volume of the cone, which is 1/3 pi times half of that base squared times 1.3 right up to the top here, 1.3. You work that out and you get 5.653 cubic meters. Okay. So the outside volume is this. The inside volume, if you subtract this one here from that one there, you will get the volume of the steel used. So we subtract the inside volume from the outside volume. And yes, we have to add the base as well. And that will give us 0.1768 cubic meter. That's the amount of steel used, the volume of steel used. Well, we know that mass is now equal to density multiplied by volume. We know the density, we just calculated the volume, and we get this as the mass. We are to give our answer in kilogram. We do have that. And we want it correct to 4 significant figures. That is to say, 1, 2, 3, 4. We want to round off at the ones position. So it is 1,340. Now, if you leave it like this, it would look like you rounded off at the tens position. So to make sure, you take half of the ones position add that here, plus or minus 0.5. So now it is quite clear that we have rounded off at the ones position, which is 4 significant figures. Okay, that was example 2. Example 3. A cylindrical building capped by a semi-spherical dome has the shape shown in the diagram at right. So this is the cylindrical part. That's the semi-spherical dome. In total, that is 10.5 meters, and the diameter is 5 meters. All dimensions are internal dimensions, so you don't have to take into account thickness of walls. 25% of the air in this building must be air conditioned every 30 minutes. Ignore the contents in that building. Calculate the airflow capacity of its air conditioned unit in cubic meters per minute. Correct the 3 significant figures. As I said, we need to develop a way to attack this question. And so the method is called reverse engineering. At first, it may look difficult to you, but if you break it down into its smaller parts, and then you combine your answers, you will find that it's not that difficult. So our plan of attack, as we said, is called reverse engineering. We will develop the steps backwards, and then we will work from the end, come back to where we need to be. So we will divide the volume of the conditioned air in 30 minutes to get the volume per minute. So we will need to calculate 25% of the total volume of the air to be conditioned in 30 minutes. Therefore, we will need to find the volume of the dome, and we can do that using this. We also find the volume of the cylinder, which is this part. Of course, we will add those two, find 25% of that, and so on. So that is our plan of attack. We will find the total volume, take 25% of that, and relate that to the rate of 30 minutes. Now, this one is not that difficult. So we will work backwards to get our answer. Volume of air in cylinder, that is this part here, will be pi r squared h, pi, times 2.5. Remember, if the diameter is 5, then the radius is half of that, 2.5 squared, multiplied by 8. So you may wonder, where did we get 8 from? Well, if from here to up there is 10.5, and the radius of this thing is 2.5, and obviously from here to there is 2.5. We subtract that 2.5 from 10.5, and we get this 8. So this is the volume of air in the cylindrical part. Now let's find the volume of air in this semi-spherical dome. Let's find the volume of air in this semi-spherical dome. It's half of the sphere. So we have to find half of 4/3 pi r cubed. Half of 4/3 pi r cubed, you work that out and you get 32.72 cubic meters. Now we add those two and we get 189.80 cubic meters. 25% of that is this amount. So 25% of that is 47.45 cubic meters, and that amount of air has to be air conditioned in 30 minutes. So we will simply now divide this amount by 30, and we get this answer here. Of course, we do have too many significant figures. You are told to give your answer to 3 significant figures, 1, 2, 3, and you get 1.58 plus or minus 0.005 cubic meters per minute. Once you understand the question and how to approach it, it becomes easy. As I said, analysis and synthesis. You break down the question into its little parts and then put back the answer to those little parts together. Now, in real life, this is just the first part of the complex calculations involved in determining the size of an AC unit for a particular building or a particular room. But I'm not here to teach you air conditioning, refrigeration, and heating. Example 4. A new athletics racetrack is to be installed at a new sports stadium. The tracks have a central rectangular shape with 2 identical semicircular ends, as shown in the picture below. Okay, this is the picture below. The length of the outside rectangle is 100 meters. That is to say, from here to there is 100 meters, and its width is 50 meters. That is to say, the width of the outside rectangle is 50 meters. The track itself is 8 meters wide, here, 8 meters wide, and 15 centimeters in depth. Calculate the cost of installing this track if it costs $12,500 per cubic meter, inclusive of surfacing and markings. Round off your answer to the nearest $100. Again, as I said, it may look complicated. We have to do something called analysis and synthesis. So we have to break down the large question into its simpler parts, work those simple parts, then put those together to get our final answer. So our plan of attack, reverse engineering. We have to calculate the total cost, and we know the cost per cubic meter. So obviously we want to find out how many cubic meters of material we will need. To do that, we will find the surface area and multiply that by the depth. To calculate the surface area, we will calculate the shape outside, calculate the shape inside, and subtract the inside shape from the outside shape, the areas. Well, to do that, the outside shape is length times breadth plus pi r squared. Now remember, it's 2 semicircles, so that would make a complete circle. And then for the inside shape, you basically do the same thing with slightly different measurements. So now we will start from down here and work backwards until we reach up there. We have a plan of attack. So as I said, we will work backwards. Let's calculate the area of the inside shape. That is to say, there is a rectangle here, as you could see, and there are 2 semicircles to the side here, which would make up 1 complete circle. What are the dimensions of these? So the rectangle itself is length times breadth. That will be this piece here, which is 100 meters times, now be careful with the breadth here, if from there to there is 50, and we subtract that 8 here, and this 8 here, which is the width of the track, we will subtract 16, so we get 34 remaining. So the rectangle itself is 100 by 34. The circle is pi r squared. Now remember, we just said from here to here is 34, therefore half of that will be 17. Square that, multiply by pi, and we get a total area inside of 4,307.92 square meters. Now remember, that is not part of the track. That is inside the track. Now we do the same thing for the outside. We find the total area now, total area, including that piece of, including that area we just calculated inside, we find the total area. So the length of the outside is 100 and the breadth is 50. That will give us a rectangle piece there, 100 by 50. And the semicircles on the outside would be pi times 25, which is the radius square. And so we get a total area. Everything in that shape is 6,963.5. So we will subtract this area here that is not part of the track from the total area, and we will get the area of the track itself. So we subtract the inside shape from the outside shape, and we get 2,655.58 square meters. Now that is the area of the track itself. But that track has a depth of 15 centimeters. So to find the volume, we multiply that area by the depth, which is, that is the surface area multiplied by the depth, and we get 398.337 cubic meters. We substitute that cubic meters by the cost per cubic meter, which is this times cost per cubic meter, and we get $4,979,212.5. You are to round off your answer to the nearest $100. So that is here. So your answer becomes $4,979,200 plus or minus $50. And this is the last example we will look at, example 5, and hopefully you would have developed a mode of attack, a way to work these questions that look difficult to begin with. This question says, a tongue's elevated water supply cylindrical tank has a shape and dimension shown in the diagram at right. So this is the diagram at right. This is a water tank that is elevated, and the tongue would draw water from it. Now, water is pumped into it from 8 a.m. to 6 p.m. only, working hours, while residents can draw water from it 24 hours per day. It is not turned off. At 8 a.m. on Thursday, the water level has dropped 2.8 meters when it was full at 6 p.m. on Wednesday. 2.8 meters has dropped. If residents used 5,000 liters per hour on average from 8 a.m. to 6 p.m. on Thursday, remember what happened Wednesday night, eh? At what rate must water be pumped back into the tank to fill it at 6 p.m. on Thursday? State your answer in liters per hour, correct to the nearest tens. And you are told that 1,000 liters make up 1 cubic meter. So, what is our plan of attack? No need to calculate the total volume of water in the tank. There's no need for that. We need to find the 2 hourly rates to get our answer. Note that the current usage is 5,000 liters per hour, so that has to be pumped in while it is being used. Plus, we have to calculate the overnight loss, which must be replenished in that 10 hours as well. Obviously, it has to be more than 5,000 liters every hour, because if you only pump back 5,000 liters, you just break even. But we have to pump more than that because we have to make up for the loss during the night, so that by 6 p.m. the tank is full right up again. Now calculate the volume of water that was lost overnight. So as I said, we will work backwards. Now what volume of water was lost overnight? It's pi r squared h times 1,000. Remember now, this h is not the height of the tank. It's just this 2.8 meters by which the water dropped during the night. So this is the height of the water that dropped. This 2.5 is the radius, because remember, if from here to here is 5, then half of that will be 2.5. So pi r squared times the height of water that dropped times 1,000 liters per cubic meter, and you get this amount of water that was lost during the night. Now that amount has to be replenished in 10 hours. So every hour you have to pump back 5,497.787 liters. But remember also that while you're pumping back that to make up for the loss from overnight, you have to also keep this in balance. So you also have to pump 5,000 liters to replace the water that is being lost during the day. So now if you add those two, the current loss, which is 5,000 liters, you have to pump that back, plus you have to make up for the overnight loss, which is this. It is already in liters per hour. So once you add those two, you have the answer. Replacement rate will be this amount of liters per hour. You want your answer to the nearest 10, so you round off here where that 9 is. Your answer is 10,500 liters per hour. And just to make sure that nobody misinterprets that you rounded off at that hundredths position, you add plus or minus 5. Remember, if you double that 5, you will get the position where you rounded off, which would give us 10. These types of problems look intimidating, but you may need to develop a plan of how you intend to get the answer before you start working on the solution. Understand what the question is asking and develop a plan to arrive at your answer. You may even use an IPO table to help you arrive at the solution. And if you're doing IT, you will know what an IPO table means. In computer programming, looks like this. Simply input, that's for the I, processing, and output. Input is what you are given in the question. Output is what you want as your answer. Now, those two are fairly easy. Difficulty comes in the processing. How do you use the data from input, from over here, to arrive at your output over here? What steps do you need to take and in what order? And that brings us to the end of this objective. We just completed objective 15. Remember, those 5 questions we did are probably more complicated examples than CXC will bring, but the website will give you better understanding of the type of questions CXC, CSEC will ask on this section. Solve problems involving measurements. End of section 4, measurements. And that brings us to the end of video 17 based on objective 15 in section 4, and as I said, also to the end of this section.